Welcome all to the eighth lecture. Let me just open up my presentation and we'll get started. Perfect. This one will go here. Sign in also too. Hmm. Let me now share my screen. Okay. Fine. So, welcome all to the session 8 of our lecture series. The course is Gas Dynamics, Fundamentals and Applications. We are at session 8. I am Shri Sahai Gupta, uh, and I am the online sessions TA for this course. Fine, let's go ahead and just look at my introduction. I am a PhD student at ISC Bangalore. I did my bachelor's from IIT Ropar, graduated in 2020, worked for a little bit in HPCL, uh, then joined my doctoral degree. Currently, I'm finishing my fourth year. Here are my contact details. I have a link to my website or LinkedIn. You can go and visit it. So that's there. Um, this introduction is mainly for people who are attending or watching this series. For like this is the first session they are looking at. So just let me see if everything is okay. Everything is getting recorded and everything is shared fine. One more thing which I need to look at is fine. So let's go ahead. So let's do a small recap of what we had been doing and what we are going to do today. So uh, the way I try to design these sessions is by way of looking at the course content of the corresponding week. This this so why this timing is not right? Something is wrong. Just give me a second. The correct time is 6, and this is so this timing thing is fine change. Let's just to close the location services. That's that. I think everything is fine. Otherwise, yeah, let's go. So, up till now, what have we been discussing? One for one, we have had looked at isentropic flows, subsonic and supersonic. We have looked, and those are one-dimensional flows. Now, what we are looking here is quasi one-dimensional. I'll talk a little bit about quasi one-dimensional flows and why am I calling them quasi one-dimensional flows when the topic is generally called as variable area flows, and how is it different from one-dimensional flows. Let me talk a little bit about that. Um, then we had been looking about from one-dimensional flows. We looked into normal shocks, moving shocks, oblique shocks, and expansion waves. And then we moved to this variable area flows. And suddenly, one thing which we would notice that our governing equations now have uh, area term uh, coming in, and it did not play a major role in one-dimensional flows, but it does play an important role in this varying area flow. So a major difference between the flows we had been looking at before and now here is that those were external flows while this is an internal flow. And that could be a bad definition because internal or external flows are majorly defined based on the viscous effects. How, like, if the viscous effects are important or not. That is the benchmark. But uh, in this case, the reason why I say internal or external is because turns out uh, it turns out that area has to come in once there is an internal flow. Now, strictly speaking, when we deal with this subject, we say that area changes and there are isentropic like the entropy does not change, but that also implies that the area changes very slow. It happens slowly. If the area changes start happening very fast, it would imply that you have some shockiness, oblique shocks could appear, expansion fans could appear, and stuff like that. If it is again supersonic, in subsonic, you won't get shocks and expansion waves. Um, but my point being that there is an inherent assumption that area changes slowly. The area change cannot be very large because, essentially speaking, we are not saying that there is a velocity in the second direction. We are assuming the velocity is always in the x direction, which we call as u. There is no two-dimensional velocity, and that implies that area has to be small. If area changes are large, you could expect the v velocity to come in, and because of that reason, because we are saying that v remains to be zero, we are saying the area is changing so slowly that from one point to another point, it has to change so slowly that there is no induced velocity in the cross stream direction, and that is why we use the word quasi one dimensional, just like how we use quasi steady or quasi steady in thermodynamic flows, thermodynamics, when we say that the process is quasi steady, implying that the flow is quasi-static, I think. I'm forgetting. Basically, the point is that when the process is very slow, we use the word quasi. Similarly, here also we have quasi one-dimensional flow, and that is the reason being that there is no cross-stream velocity. That is an important distinction between the flows we had been dealing before and the flows we will be looking at today. Okay, fine. So in the last lecture, we had been looking at the same topic, and today also we are going to focus on the same thing. So I'm going to spend a little more time on the recap today so that we make a good foundation for people who have not watched earlier videos or maybe are lagging on the video lectures as well. So what we would note is once we write and governing equations, these are the three governing equations you will be able to write. In fact, this is not the governing, this is not the energy equation. This is just a statement of the momentum equation, but this is the this is the momentum equation, and this one is conservation. So this is just a restatement of. Let me admit someone. Someone is, yeah. So as I was saying, this is a restatement of the mass conservation equation, while this is momentum equation. Energy equation still remains the same, dt plus uh, uh, d of u square by 2 equals to 0. So that stays the same. Now, following these three relations and the energy, this ideal gas equation of state, we actually in the last class derived these relations. And so we wanted to see if there are area changes, how the Mach number varies, how will the temperature would vary, how the velocity would vary, density would vary, pressure would vary if there is a change in cross-sectional area. And that was something that we spent a little time on. While um, uh, the second problem we did was a little more well, it was a numerical, and so the whole point of that numerical was um, of two basically emphasizing on two relations, that the total pressure loss is directly related to the entropy change that happens in an non-isentropic flows, and we will also see maybe today I will emphasize on it better today, that across a non-isentropic flow, we see that the sonic area, we're trying to call it A star, let's not call it sonic area, let's call it, people call it throat area, but let's call it A star. The summation of the multiplication of A star with total pressure remains constant. We'll see that today also. We kind of used it in this problem as well. So these are the things that we looked at. Um, now, let me now, because Pranav is there in the chat, let me first ask him if he has any questions for me, or otherwise, should I keep going on? So, Pranav, are you there? Are you able to hear me?
Yes, sir. I was actually
Yeah,
traveling. I just got home. Yeah.
wait, I'm not able to properly hear you. I'll
No,
use.
no, uh, uh,
Yeah,
no,
yeah,
no. I was
I
actually
can hear you
traveling,
that
so I got
you
late
saying
for the
that
class.
it's okay. Just let me see if this will work. Okay. Can you just speak one last time? I wanted to check my headset.
Hello, hello,
Great.
hello. Yeah. Okay.
Yeah. Were you did you watch the last session last week's session, or do you have any questions? No, right?
No, 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 sir.
Great. Okay, let's move ahead. Uh, when we go and so basically, okay, for the benefit of Pranav, we are basically continuing our discussion on variable area flows, and towards we are going to talk about application. So when we go ahead and talk about applications, the first application does come from the converging diverging nozzle, as we will see today. Couple of questions, majorly all the questions will be on the converging diverging nozzle. We'll see that if there is a supersonic nozzle, um, depending on the back pressure or the exit back pressure to the stagnation pressure ratio, the flow is dictated by this ratio. If this ratio is a small number, uh, the entirety of the flow will be subsonic. But actually, it's not a fine. If it's a small number, then the entirety of the flow remains to be subsonic. And if it reaches a critical value, then we'll see that there is a sonic flow at the throat. If we go lower than that, we'll suddenly see that there is a normal shock that starts appearing, uh, and that will, as you decrease the pressure ratio, you'll see that this normal shock will move towards the exit of the nozzle. And
it will do that. So once it moves and it reaches the exit of the nozzle, it can be called as a second critical thing, from which the expansion operation of the nozzle starts. Um, there will be a normal shock at the exit. If you keep decreasing it, you will start experiencing that normal shock will uh, will convert into oblique shocks, and depending on the strength of the shocks, we'll see that. And this, whatever these shocks are there, basically what is it doing it just before the exit of the nozzle and just outside of the exit of the nozzle, there is a increase in the pressure. So this shock is basically increasing the pressure rise. Sorry, is facilitating the pressure rise. And so we see that just before the nozzle exit, we have expanded the nozzle too much. We have expanded the flow too much so that a normal shock is compressing it back to the back pressures or exit conditions. And so in this region, we call it as overexpansion. If we again reach a third critical pressure ratio value, you will see that there will be no shocks and nothing. Basically, the normal shock strength will continuously decrease. It will become oblique shocks. As we had discussed in the discussion on oblique shocks, we saw that there are two solutions. The strong solution, there are like for theta equals to 0, there are two solutions. We one the strong solution is the normal shock, whereas in the limit theta tends to 0 and the pressure ratio across the shock is close to 1, you will see that there will be only small Mach waves. And then close to that, you will reach the third critical condition. If you further expand it, if you see that the back pressure is lower than the exit pressure, or just before the exit pressure. Just before the exit, the pressure is still higher than the back pressure. You'll see there will be expansion waves. So expansion fans, and that is how the flow will expand to a lower pressure. So that just summarize this thing, because we'll see we can have some discussion on that. So probably let's just discuss it. So that is why I did this discussion. So now let's move to the questions or the numericals that we'll look at. Okay, fine. Let's start with this problem 0. So there's a one-dimensional steady flow of a perfect gas, horizontal system, no shaft work, no frictional losses, but area changes and heat transfer effects are present such that the flow is at constant temperature. And now we are asked to derive certain expressions for the static pressure ratio, total pressure ratio, area ratios, and also area by this A star ratio, and what is the Mach number at float. So we'll look at how we'll see how this problem evolves. So let's first look at the expression for static pressure ratios. So first, let me just quickly draw what is going on. You will have some weird shape. Let me see. Yeah, so some weird shape, and it's just not. Let's say it's something of this sort. Maybe I'll flip it. Yeah, but it's not insulated. That is the thing there. So there is a flow in this direction. So now we have to again derive everything based starting from the governing equation. That is mainly what the problem is around. So just let it be. So let's discuss what are the governing equations we have. So we have you can see, so UA is a constant. This one is fine, but okay, this is okay. Then we also know that dP plus rho u du is constant, very similar to the variable area flow, only that the energy equation will now be different, because generally the energy equation has to be this. Okay. Generally, we know it's adiabatic flow, so we don't consider dq. We say it's a zero. This one also will be zero. And because now we know that the uh, heat transfer, whatever the heat transfer is doing, will dictate that the temperature remains constant. Simply, instead of solving for energy equation, you will get the temperature constant condition. That is just from the like this problem statement. So now if we begin and note that now we don't have an expression for area, and area does not appear in this formula we are trying to derive. So a hint here is that we want to remove the dependence on area. So maybe this problem can be thought of about like in this manner that uh, area changes causes temperature changes, but heat transfer is designed or is made to happen such in such a way that the temperature remains constant. In that limit, in that condition, what is going to happen? That is what we are trying to understand with the help of this problem, and I think that's it. So now, basically, now we need to substitute for the area changes. So what we have here is, now just try this thing. I have one more condition here. Oh, okay. As I was saying, we have another condition here. We know that temperature remains when temperature remains constant. We have an expression for between P and rho. So we can use that. So it's basically P by rho is a constant. And so what we have here is dP by P is equals to d rho by rho. Yes, that's all right. So if the temperature increases, so will the density. If you think by rho is this dP minus, I think this is okay. If pressure increases, so will the density. That's true, right? When the temperature is constant. So now what we can do is at T of rho u by, or let's say 0 up, yeah, 0 by rho u by u plus dA by A is 0. Um, let's start substituting things there. You can see I can substitute dt by P here, and equals to minus dP by rho u from this expression. So I'm gonna use this thing to write du can be written as dP by rho u. So dP by rho u, and there is a u again, so rho u square. I think there is no issue with this step probably, and that's it. So if that is fine, what we have here is is there. So A by A, U square by this thing. Now, on right, okay. Does anyone know how to proceed? I'm kind of missing how to proceed. Let me think about this problem. Meanwhile, if anyone has a suggestion how to proceed, we can discuss that. We think meanwhile. Let's start doing this. U square is gamma RT. That is there. Now this rho RT becomes P. So it's gamma P. So you can actually take 1 by P common. One there. I think that's it. Okay. Um, okay, fine. Check my notes. I did this. I've forgotten. And it was a mistake or something. So does anyone see a problem with the solution, the way I'm going ahead or anything? Only you are there, I guess. So do you have any comments to make? See where I've kept my notes. Not straightforward. Probably not. Thanks. Okay. What we can use here is fine. So let's just go ahead and write this thing down. So this is d ln p equals to d ln a, and this is just simply this term. Okay, it implies that p2 by p1 is a2 by a1 to the power of um, oh, wait, we can't just simply integrate it because Mach number is a property here. Wait. We can't actually use this. I'll go ahead with this. Let me think. This is time. Say du becomes minus here, man. Yeah, minus is this is also the minus. No. Let me do this thing again. We have dp by p plus, so du becomes minus dp by rho u by u is dA by A. Basically, this is this was 5 4 B whole square plus EA by A. Let's see. Hmm. Rho U square again, I can write it as gamma RT. Let me write it here only. Rho RT is P, so gamma P. Mhm. Uh, this one is okay. The earlier expression was fine. Now, this is earlier expression was okay. Pressure is this pressure changes with area this much, but uh, okay, fine. Let me substitute this thing.
So can we make use of that steady flow or the energy equation that's dq dh plus u du?
Okay. So for that, let's say we use this. Essentially speaking, so first tell me this. First confirm if this is okay or
Actually,
not.
actually,
Yeah, go ahead.
the temperature would be constant, right? So maybe,
Yes, the final thing from that
yeah,
will only be the temperature is constant. Do you see any problem with the steps I have taken up till now? So basically,
the
this is, yeah,
now the Mach number,
yeah,
the Mach number depends on the temperature locally. So
yes.
if
Hmm.
the temperature is constant, then a Mach number, sorry, the not Mach number, the speed of sound would be constant at
Yeah, that I
all
have not
points.
used. Yeah. See, interesting. See, that is what I was saying. So, um, a square is dp by what is it?
dp by d rho.
Consider what? Yeah. See, so no frictional losses, no shaft work, but area changes and heat transfer. Yeah. So it's not an isentropic flow though, right? So it's gamma RT only. Can't use that, I guess. That's it, right? So basically saying that speed
Yes.
of sound is gonna remain constant. It's not gonna change, right? Across the entire flow, speed of sound is not gonna change, right? A square is a constant, and only the velocity is gonna change. So Mach number Q by A. I did this problem in a somewhere in my notes. I let me see. Yeah, see here only. Let me see. Good of me not have checked this. This Hey, just a second. Maybe the problem is. Wait, let me check the problem first. Have I made a mistake in writing the problem? Just give me a second. problem is fine. Fine. This one more thing that we can do is, let's see, why are we getting stuck? Let's try to understand that. What all formulas have we used? I'll just highlight what all equations we have used yet. Have we used this? No, we have used this, right? It's basically this one. We have used this one. And then we have used t equals to constant. I'll mark that with a different color, which is essentially this. And we have also used in writing this thing, which is green. So this one, we have substituted du using this green equation, isn't it? So that is also okay. Then what is this? Let me see dp by rho is yes, yes. Okay, okay, fine. Maybe let's see. Okay, so the way I did this problem before was in this manner. Let's see. So I use this green equation. Okay, and I wrote it down as, and you get this, right? When I write this thing down, this is fine with you, right? So now if I go ahead and write a next step to it, now using that temperature is a constant, this is gamma RT, you can actually take RT, gamma RT outside to get this, and actually I'll take it down here so that I'll get dp by p. This is the expression that we should have got. Now, simple. Now it's very simple. It's ln p by gamma is what? Minus dm square. So what it is gonna give you is ln p minus m square plus some constant. So now the way to remove this constant is take two boundary conditions so that you will get ln p2 by p1 is going to be yeah. And now you can see, oh wait, there is a 2
I
also which
think
I
you missed
missed.
the two from.
Yeah,
Uh,
yeah. Understood. What I am surprised about is why we were not able to get this otherwise. Like, why did we like maybe we added a unnecessarily added this area which we don't know any information about. So maybe because of that there is an issue. Okay, fine. Uh, but this is also acceptable, right? The way we did this is also acceptable. So finally, what do we get is P2 by P1, uh, e to the power minus, and this minus can be absorbed. Let's not absorb it, let it be. So we got this expression. Okay, so that is for the first thing that we did. So in the next week, you will see that you will study friction effects, and you will also study effects of heat transfer. What you can see is that you can make combinations and permutation and combinations of any two out of these three effects, and you will see that these kind of relations are going to be used. So it's just a simple problem of showcasing that. Anyways, let's go ahead with it. Let's see what is the ratio of total pressures. So that one is, I think it's a little direct. So let's do this. I'm sorry. Um, that is a little direct, I think. Mm, um, to that one. One thing, Pranav, will you help me write the expressions for these three ratios? It's pretty straightforward, maybe not. One more thing, how is the lectures? How are you liking the lectures? Are the lectures fine? Not like my lectures, the
Yeah,
video lectures.
they are fine. Yeah, it's, it's,
Ah, you were saying something.
no, no.
Okay. This is the expression, right? This is the general expression because
Yes.
total pressure to static pressure, we can do that isentropic thing. Again, same thing. Yes, there will be a minus sign here. So just we'll note that. And what else? And then we'll substitute this expression also. I think it's a pretty straightforward thing. Now, so similarly, we can just have a just let me check if the expression that we get is something else or what form do we get in. Let me remove this. Yeah, yeah, it's fine only. This is the expression we get. Um, yeah. So now we can actually use, and now that we have these expressions, now we can use this relation to find A1 by A2, right? Uh, how do we do that? We see that dP by P is actually related to M. Okay, so we are going to use that. So no, yes. So let me remove a couple of expressions from here. This and this. Okay, so I can take this gamma and put it there. And then what do we have? Right, there is a minus sign here. So let's absorb that minus sign place. Mm, actually, there is a better way to do this. Let's do that. Let's forget about this. Better way to do this. Let's do that. Rho RT is just P. So that is there. Actually, you're going to get the same thing. Gamma also we can remove because it's a derivative, so we can just remove gamma also. So what we'll see is this. But so this implies that A1, yeah, that is C. This is a simpler way to look at it. So now we know P2 by P1. And now just here need to multiply that expression. That's just this straightforward. Um, Let me just check if the expressions are fine or not. Now comes this discussion of A star. So A star, what we will see is, see, up till now you have studied only variable area flows, and A star directly relates with the throat area. What we will see is A star will also, A star is much more related to sonic conditions. Okay. Although it is related to throat area right now, you'll see that it is also related to sonic conditions. And no matter what mechanism is, if there is a mechanism of area change, or if there is a mechanism of friction, or if there is a mechanism of heat transfer, you will see that these mechanisms can drive the flow to sonic conditions if applied in the correct directions. These any flow can be driven to sonic conditions using these mechanisms, and A star is the final, like it's the condition where the flow will become sonic by these mechanisms. For different mechanism, A star will be different. But right now, the definition of A star is related to Mach number equal to 1. So just to use that, we can actually find A by A star by just simple substitution. So A1 by the function of M. Let me just write it down. So I have to substitute M2 as 1 and M1 as M. So that will be 1 by M, and this is expression. Okay. That's fine. Um, yeah. Okay. So now it says find the throat area. So again, the throat area here, the throat area will not be related mm, to sonic conditions. Throat area is defined by dA by A equals to 0. In fact, to be precise, it has to be d square A by A square has to be negative also. That is also something that we can show. I don't know if we can show that. Should I spend time in showing that? Maybe it can be an exercise. What do you think, Pranav? Let me complete this and then we'll talk about that. Okay. So we know A is a function of A star. A star will is a kind of a constant. It does not change as long as the flow is isentropic. Wait. As long as flow does not have to be isentropic. You see, A star is a constant because A star denotes a condition where the which corresponds to sonic condition. So A star is kind of a constant. It won't change. Uh, won't change with what? So wait. So this is the thing there. If I write, wait. Let me see if this is what they're asking. Hmm. Okay, so let's look at this the other way around. We see that we see that dA by A is equals to minus dTm by Tm. Okay, uh, this thing will be zero when dPm by Pm is also a zero. Generally, we for minimum area, we also have to imply that P square A by A is a negative number. But let's skip that for meanwhile. Let's just say we want to find out the solution to dPm equals to zero. Right now, you can see that for that to happen will be dP by P plus dm by m, the constant there. We know what dP by P is. Yes, so now dP by P can be written as a function of m, is it? Or should we use this condition? This is also there. Let's say I use this. Let's say I write A equals to A star divided by m e to the power. I write dA by m dm is 0 uh, across the throat area, across the area with minimum, across the region of minimum area. We know that no matter how the Mach number changes across it, area changes 0. So that we can use this expression then to write what? By dm is what? N times right? This is what you will get, right? Gamma m square. Has to be 0, implying that These two things have to be. This thing will get cancelled. This exponential term will get cancelled. Mark number gets cancelled, and we will get Mach number equals to 1 by gamma. 1 by square root gamma is the Mach number of minimum. That was the problem actually. I didn't write it down, but the problem was to define to see that minimum area occurs at Mach number equals to 1 by 1 by square root gamma. That was the problem. I didn't write that down. I just wanted to see the expression of minimum area. So this is the nth node. Anyways, first let's try to understand why A star is a constant. Pranav, can you tell me why A star was kept as a constant? Or what do you think? Is it a constant or not? Is this derivation fine or not?
So if we have any any duct of varying area, so
And also
at
heat
a
transfer
certain
taking place.
yes, yeah, heat transfer taking place. So the A star would means if the flow is established, then at
Right. A star will imply
so
that the area at
A
that
star,
particular location. And yes,
yeah, it won't change. So we
it
can
won't change.
consider it as constant because the Mach
Great,
number is
great.
one.
Yes. The Mach number is one, and also it signifies a particular value. It does not signify some variable. It
Yes.
signifies the
Anyway,
area, uh, yeah, corresponding to Mach number. So yeah, that is correct. That understanding is fine. Otherwise, it would become a little difficult if we continue and use this way. We need some reference node. So this is the reference node. A star becomes the reference for this flow. Fine. So this was problem zero. Now what we are going to see is a couple of simpler problems, not difficult. So let's go about that. Fine. So what is these are simple problems. So we'll quickly go over them. Consider isentropic subsonic supersonic flow through a convergent divergent nozzle. The reservoir pressure is 10 atmosphere, 300 kelvins. There are two locations in the nozzle where area to throat ratio is 6. One is in the convergent section, other is in the divergent section. At each location, calculate Mach number, pressure, temperature, and velocity. Okay, so I've written down the required formulas also. So instead of using the table, just like how we have been doing up till now, we'll use that graphing website to see to find the solutions. Let me open that website and yeah, I'll just open that website. We'll plot this graph, this function which I had just shown. Let me share my screen right now.
so actually, I wanted to ask something
Hmm.
about the assignments.
Go ahead.
So
Yes, yes.
there were some questions like of
Hmm.
varying area.
Hmm.
I think the previous week or the one
Should I
previous to that.
open? Oh,
No, no,
okay.
I don't remember which question is that, but there
Okay.
were a few questions in which like I didn't find any other way to to solve them. So the questions were like you have to find the area ratio or something like that. No, no, sorry. I think the area ratio was given, and you have to find the Mach number
Okay.
at a certain place or something. So yeah, it was a CD nozzle, I think. Area ratio was given. You had to find the Mach number at the exit or something. So I didn't find any other way to solve it. Because now what happens is that when we apply the area ratio formula, now it
Hmm.
becomes very tedious to solve because finally uh, it is a very, what can I say, that equation can be solved using solvers and not like traditional algebra. Like,
Okay, okay. I got your point. What
so
you're
if
saying.
such
Hmm.
questions yeah come
Come.
in the exam,
How?
how can I solve?
Okay. So there are two ways to look at it. The practical one is that you are not going to get any problem, at least in the exam, that you can't solve. So you can at least be assured that something of with gamma, you will get a property table associated with it. That is mostly the case in Gasdynamics courses, that you always get a property table, and that property table will have A by A star ratio as a function of Mach number. That is the first thing. That is, but suppose there is a like suppose you have to do it by pen and paper. How do you solve a transcendental equation? Basically, you're talking about you want to find uh, it's a implicit equation. It's not a transcendental equation. It's a implicit
It
equation.
was actually it was a nearly an equation of power 6.
Power
So
six. Yeah. So
yeah,
it diverges very far. That is your concern, right?
yeah. Means in that
Yeah.
time frame, how can I solve it?
Yeah. So don't worry about the fact that it will require you time, because generally in such cases, you would get a table for that gamma. Basically the issue is that for property tables are generally given for 1.4 gamma value. But if you have some non uh, air kind of fluid, then what? How do you do it? See, the simplest answer to your problem is guess. See, suppose let's say let's let me oh let's try to do this right now. Let's try to do it numerically. Let's not do it by graphically. Let's try to do it like let's do this by hand like this. Suppose that we were doing it. Okay, let's use a calculator or something. Okay, we'll not use it. Use the graph. Okay, we'll solve this problem itself, and we'll see the way. Again, the time could be we could take a way, and this is called hit and trial. And not hit and trial. Basically, you're going to start noting down values for different mark numbers, see where you can converge, and that is how you do it. So in exams, generally, if you get a little unlucky, if you start with a very bad guess, you won't converge to a good solution, or you won't converge at all. But generally, after say, several iterations, you will reach your solution. So let's try to do that. And it's a good point. Not plot. I'll not plot it today. Let's try to do it this way which we discussed. I'll share my screen first. Hmm. So yes, the formula I have is uh, take a screenshot. It says there's no point of taking a screen. You won't be able to see. So you can see this graphing website, right? So
Yes,
we
yes, I will
have
see it as well.
this. I'll just write this formula for you. So we have 1 by Mach number square. Okay, then 2 by G plus 1. Just check if I'm writing it fine or not. Okay. Probably I'll write it okay. I'll just check if I'm making any mistakes. And this is the formula. So I'll take a G value of 1.4. Okay. Not going to plot it. That's why I wrote M Mach square, not X square. Otherwise, it will get plotted. And the area ratio given to us is this is 6. We want a value corresponding to 6. Okay. Okay, I'll now narrate the problem once again. So consider an isentropic subsonic supersonic flow through a convergent divergent nozzle. Reservoir pressures and temperatures are given. There are two locations where area to throat area ratio is 6. We need to find the Mach number associated to it. Okay, so we know A by A star is 6. Okay, so that also we know. Now let's do it. Suppose Mach number is 2. Suppose M is 2. What value are we going to get? So for can we add a table here? Yeah, we can add a table also. Good. So for Mark 2, the value that we get is 1.687. That is how you will have to do it in exam. Okay. Now let's also do it. We know, acha, one more thing that we know is for Mark 1, the area ratio is 1. Okay. What else? I don't know if you're able to see the screen. Screen is fine, right?
Yeah, yeah, I
Yeah.
can see that as much. Yeah.
Yeah, yeah. So now let's do it with 3 also. What is the value for 3? For value of 3, it gets 4.23. So now you know where we need to move, what next value we need to take, right? See, it's getting plotted also here, right? It's getting plotted also. So we know now we need to go near to a value of 6. So let's take 4. Again, you have to do this calculation. Right now, I'm doing it using a this calculator, so it's pretty fast. Like using a software, you would have to keep doing it using that scientific calculator. That's a bit tedious. But again, the correct way, like the official way to do it is this way only. So that is 10.7. So now you see we have very quickly moved way past that value, 10.71. So again, now simply like this is called bisection method. If we have to numerically find this value, if we do 4.5, what value do we get? We get wait. So 3.5, sorry, not 4.5, 3.5. So for 3.5, we get a value of 6.78. Okay, maybe 3.3. Let's try with 3.3, 5.62, 3.4, 6.1, 6.2, 6.18, 3.35, and so on. You get the idea now, right? You get that idea.
Yeah, yeah, got it.
Yeah, 5.9, right? So, right
Yeah.
now I'll stop. I'll just see there are multiple iterations that you will have to go through. That's true. That is not going anywhere. So the move is now let's see what value.
Actually, that's the biggest issue actually, because now in
Don't
the NPTEL
hmm,
exam they
hmm,
give very basic calculator. Like it is a scientific calculator, but
hmm.
I think you cannot use the keyboard. Like you cannot type fast. You have to click and click. Think you cannot. I think like we have cursor here. We can move anywhere left and right. We cannot do that. We have to type it in the one go. I think.
Acha,
So I
tell me
don't
one
think.
thing. Tell me one thing. Do you know how this tables are going to be provided? See, don't worry about obviously when they're planned NPTEL course, right? They know that this, and especially with guest dynamic courses, everyone knows that people are going to use tables. What you can do, a smart thing
They
that you can do is stop, like don't interpolate. If you have some time, small time, don't interpolate between entries of the tables. Okay, just use the nearest entry. That is also fine.
they may
Hello?
provide the property tables
They will.
in the question. Yeah, I hope
I
they will.
don't. So they will definitely. No guest dynamics course can work without property tables. Nobody. You even know like any textbook will have property tables. Any book. It
Yeah.
cannot work otherwise. Because now we have computers, but you don't have that. What do you do? So see, we get two values of Mach number point 0.097 and 3.36. So we were pretty close. We tried 3.35 as the last value. But again, uh, I get your point, what you're trying to say. So yeah,
Yeah.
I'll just note down these two values. Let's stop sharing the screen. Right. We get two solutions. 0.097, 3.36, some value. We won't care too much about it. We can calculate. So we know stagnation pressure also. So P subsonic will be what? 10 atmosphere divided by 1 plus 1.4 minus 1.2 into 0.097. Just write the value. So let me just do that. So we can plug in those values. I'll just tell you the value. It's just plugging in the values. This question, nothing rocket science. To think about it, that is the problem with this Gasdynamics course. It requires extensive use of computer. And there are a lot of formulas as well. You mess up anywhere some entry, you'll get a incorrect answer. So that's an issue. Just tell you the entries, then we'll move ahead. So Mach numbers were fine. 3.368 was the supersonic value. Subsonic value was 0.097. For the subsonic Mach number, the pressure you're going to get is 9.94, very close to 10 atmosphere. Obviously, because Mach number is also very close to zero. For the supersonic Mach number, the pressure, the local static pressure you will get is 0.159 atmosphere, which is very low. A pressure ratio of almost 10, right? Um, not 10, much higher. I don't know. 63. Yeah, it's 63. Then temperatures also similarly, the subsonic value will be uh, close to 300 kelvins, and it is actually 299.4 kelvins, and so on. So that's the first problem. Whole implying that given the flow is entirely isentropic, we can use these formulas. That is what this problem was about. Let's move to the next problem. Okay. A supersonic wind tunnel is designed to produce 2.5 Mach flow in the test section with standard sea level condition, calculate the exit area flow and reservoir condition necessary to achieve these design conditions. Pranav, would you like to initiate this problem? Do you want to tell me how do we approach this?
Yeah, I think the area ratio, yeah, these formula, the area
Ah,
ratio, we have the Mach number. So from that we can get the area ratio.
okay, let me just go and see what is the area ratio corresponding to Mach 2.5, right? Check. The area ratio is 2.63. 2.63. You can see my, I don't know, you need to see or not.
I cannot see the decimals, but I can see the PPT.
Yeah, PPT is fine,
If-
right?
Okay.
2.63, right? 2.63 you get. Now what? Now what
Now,
do you
yeah,
do next? Yeah.
calculate
Now
exit area, reservoir condition necessary to achieve these.
we need to calculate stagnation conditions.
Yeah.
Acha, okay, what else is given to
Mm,
us? P static is given to us. Static pressure is given to us is 1 atmosphere. Temperature is also given to us as, let's say, 300 kelvins. Standard sea level temperature is 298, I guess. 288, 15 degrees Celsius. fine. That is okay. So 288, right? 288 is 15 degrees Celsius. So now just simply again putting up the formulas there, you'll get the reservoir conditions. Okay, you'll get a reservoir temperature, reservoir pressure, and yeah, that's it. You can also calculate reservoir temperature also, right? Just using this formula. So P naught by P is given to you, and T naught by T just so just that simple stuff. Let me give you the values so that we can have a little bit feel of it. So you see this reservoir temperature pressure will come out around 17 atmosphere. Temperature is gonna come about 650 kelvins. So pretty high values, right? This implies that if you want to design a supersonic wind tunnel and you're going to use it as a blowdown facility, you have to severely heat the reservoir to 600 Kelvin. 600 Kelvin is what? Uh, what is 600? Yeah, 600 Kelvin is 450 degrees Celsius
Usually
or something.
400, 450.
Yeah, 400 or something, some value, 400. And then pressure is 17 atmosphere, 17 times higher than this thing. Okay, so that is one insight that we can take from this problem. Simple problem, nothing very fancy. Let's go to problem 3. Okay. Consider a rocket engine burning hydrogen and oxygen. The combustion chamber temperature and pressure are these values. The molecular weight of the chemically reacting gases in the combustion chamber is 16. The specific heat ratio is this. Um, the pressure at the exit is given to us. Area of the throat is given to us. And we need to calculate the exit Mach number, exit velocity, mass flow through nozzle, and area of the exit. Maybe we can do this problem and properly. Okay, so let's do that problem. But now that this rocket engine has come up, um, what do you think, Pranav? In a PSLV or any rocket engine for that sake, uh, atmosphere, how does your nozzle exit go? Like, will it go from over expansion to under expansion or under expansion to over expansion? What will happen?
It's actually, oh, they keep it over expanded. So,
The key.
uh, so at an altitude, they design it for a certain altitude. At that altitude, it becomes optimal. Then it starts becoming under expanded.
Later on. Yeah.
Yeah.
So it
So just
starts as
for some
overexpanded.
altitude amount.
It starts as overexpanded, then it goes to that optimal value, which is the third critical, I guess. That is what you mean, right? And then it goes to under
Yeah, yeah,
expansion, right?
yeah.
Okay. Nice. And why do they design it? And how do they decide? I think you know a little more about that. How do they decide this altitude and why do they do it? Obviously, they have to do it overexpanded because yeah, they can't just yeah, it won't make sense because the entirety of it cannot be underexpanded. The entirety of the ascent cannot be underexpanded. So they have to design it as overexpanded. And yeah, but how do they decide that altitude?
They take
Not sure.
pressure measurements over the altitude. So the back pressure would decide the over expansion
And
or under expansion.
can they ensure optimal operation in across the entire ascent or takeoff or whatever we would like to call it, entire journey?
No, they cannot. Well, if someone invents a variable conversion casting nozzle, then they may try and make it
Hmm.
optimal.
Yeah,
but
yeah, yeah.
they cannot because there are divergence losses.
There are divergence losses.
Huh? Haha.
Divergence losses, is it?
Yeah, yeah.
What are those? You mean these
The,
losses outside?
due to the yeah means there is an angle at which the gases exhaust the nozzle. So that's why they
Hmm.
try to make it at an angle zero at the exit if it is a parabolic nozzle. But we have a conical nozzle, so I think there are some small amount of divergence losses.
Okay. Yeah, I don't know much about it. Good. Nice. Okay. Great. Yeah. Conical and parabolic. Basically the shape, right? Okay. This is something that we'll discuss
Yes,
later
yes.
on. Anyways. Yeah. So now let's do this problem. Again, very straightforward. What is it? First, we need to calculate the R value. 8.8314 divided by 16. Let me just calculate that value. What's the molecular weight of air? 28 something, right?
28.96 something.
Yeah. How much is it? 28.96. Yes. Now 314 divided by 16 is how much? 519.625. What else? Specific heat ratio is given to us. Gamma is given to us. 1.22. The pressure, exit pressure is 1.0.00174 atmosphere. Throat area is also given to us. I think throat area is yeah, throat area is 0.44. What else? Yeah. Acha, okay, one more thing. Combustion chamber. We'll consider the combustion chamber to be a reservoir. So P naught is how much? 25. So if we use this, find a Mach number, right? We do this. It's quite a very high ratio. Let's say 4. What is this value? Okay, so let's use this value. I'll use my this graph calculator. Let's do this. This is the formula for this thing. And
Sir, what was
we
I
need to,
supposed to find in this question?
oh, the question is a couple of things. We need to find the exit Mach number, exit velocity, flow rate, and the exit area. So because You're considering, yeah, it's given that the flow is isentropic. So we can use the isentropic relation. Get a very high value, which corresponds to what? Oh, no, this cannot be this high. Wait, wait, wait. Something has to be wrong with this. Let me check. Let me check. It has to be wrong. Oh, gamma is 1.2 also, and R. Sorry, atmosphere, exit pressure is this much. Actually, a very high value. Whereas this Mach number goes high, the values are phenomenal. So I'm seeing what is this value?
I got
This value
exit
is
velocity
what?
with nearly 3896 meter per second for exit.
You calculated, is it?
Yeah,
It's close, yes. It's close. How did you calculate it? Did you do it any other way, or did you follow that Mach number calculation only?
I use the steady flow equation directly. From that, we get velocity. Applying stagnation condition, we 1 0, so we get exit velocity directly. We have the pressure ratio. We have P exit and P naught, so we
Yes,
can directly get the value.
yes, yeah. So you used, no, but wait, wait, wait. How did you do it? Tell me. What steady flow equation you
So
used? What is the steady flow
means the
equation you used?
so H1 minus H2 plus half V1 square minus V2 square is 0. So I didn't consider any heat or work done.
Yes,
Then
that
from that we get H1 minus H2 equals half V2 square minus V1 square. Considering
yes,
stagnation condition, V1 is 0. So from that
yes.
we get V2 is 2 into under root uh, 2 into under root Cp T2 by T1 minus T2. That
To know the temperature also. Yeah. So that is fine.
from
Okay.
temperature we can get pressure. From temperature we can convert the T1
Yes.
minus T2
Pressure. Yeah,
into
yeah, yeah.
ratio
Yeah.
and then from that
That's
pressure.
fine. That's fine. Yes, that's correct. That's correct. That's correct. It's fine. So from this Desmos one, I'm getting this value of Mach 4.96. So Mach number of 4.96 I'm getting, which is actually very far from what the other value is. How much should be 0.114? Right, that's right. Yes, now I'll get that. Yeah, so we get, yeah, this is what you will get. Mark number is, you can just, your way was fine, was actually correct. So this mark number you'll get is 5.21, and then just how you said it, TE by T is related to pressure ratio. So if we use this, and I'll just simply write the exit temperature. exit temperature comes out to be 885.3 Kelvin. Then, as you said, you can use this to find what? Find the speed of sound. That will be 749.1 meter per second. And then you multiply it by 5 times. So you got something. What value did you get?
Got 3896.11 meter per second.
3896. Yeah, 3896,
Mm,
right? And that
yeah.
is roughly what you will get by multiplying ME into AE. This is the speed of sound there. So the exact value is coming out to be 3903, but I will consider it fine. The value you got. What else? Yeah. Acha, how will you calculate the flow rate? Straightforward only.
Yeah, we can,
We also
what we
have the
have
throat area
row.
also. So we just need to find the
Yes.
density. That's it. Nothing much.
Rho
You know,
is P
press.
by RT.
Yeah. Yeah. Again, that is a very big assumption because at these high Mach numbers, nothing is going to be that valid. All
Yeah,
dissociation and
yeah,
everything is high.
but we
But
consider ideal.
yeah, yeah. So if we consider that, the density you're going to get is how is the problems how do you assess the level of the problems in the assignments? Not the assignments that I've been discussing, in the assignments that you have to submit.
Yeah, they are, yeah, means they are some of them are a little bit difficult, but
Okay.
we can solve them if we put in some more time.
Sir, I think it has discussed the need for a diffuser to a good length, right? In a supersonic wind tunnel and stuff,
Yes,
diffusers.
yes.
Yes. And what about this aspect of it? Just give me a second. That normal shock is in fact a very good diffuser by itself. This statement to you, do you relate with this statement?
Yes, it is a very good diffuser. It's like a very quick diffuser, but it comes at the cost of temperature. The temperature
Yes.
rise
Well, not temperature, it's
or
basically
entropy.
total pressure loss. Yeah, entropy.
Entropy.
Entropy is. But if you think about it, uh, the way diffuser efficiency was defined, this was the baseline diffuser. Normal shock is a baseline diffuser when we compare diffuser efficiencies. And at low subsonic flows, that efficiency, you can get good efficiencies, diffuser efficiencies. But for high speed flows, for hypersonic flows, near hypersonic flows, the best you can go do is a normal shock. So yeah, hmm, I think. Acha, tell me, Acha, sir, I think sir has discussed this part also. Not very. This thing sir has also discussed. Why you cannot have a totally isentropic nozzle, converging diverging nozzle, such that the exit back pressure and exit the back pressure and the reservoir pressure, total reservoir stagnation pressure in the reservoir and the stagnation back pressure is equal. Can we have that condition? No entropy loss. It's um, the flow accelerates through a nozzle and then is diffused to again back to reservoir condition, like same reservoir conditions.
Sorry, I didn't get the last part of this.
So I'm saying, can you have a totally isentropic diffuser? You can definitely have a isentropic nozzle if, yeah, but can you have an isentropic diffuser? Totally, total, like, and zero entropy loss. See, the reason for this normal shock to be a baseline diffuser is that uh, there is entropy loss associated with the normal shock. Then why can't we have a diffuser which is like no entropy loss is there, 100% pressure recovery, total pressure recovery? I think sir has discussed that part as well. What do you think about it?
I think I don't remember.
You
I
don't
may have
remember.
seen.
Acha, okay. Let's think about this. Like just do a like thought experiment. I don't know. Suppose there is a reservoir. Okay, some P naught pressure is there, and now you accelerate it to a nozzle. You have a test section where you want some high Mach number flow, and now after behind of this test section, now you want to expand it, not expand it. This, yeah, compress. Wait, do you compress it or expand it? Pressure, static pressure, velocity decreases. So yeah, compress it. Let's say compress it in a diffuser. Do not use compress, but we should use slow down. So now we want this high Mach number flow to be slowed down to again zero velocity. Can we use a like a variable area duct? Again a variable. So suppose there's a converging diverging nozzle. Now can we use a diverging converging diffuser to diffuse it to stagnation conditions so that there is no losses at the end of the diffuser?
Um,
Well,
he actually was discussing about normal shock inside the diffuser.
he was discussing what? The normal shock inside the diffuser, is it?
Yeah, means if it is designed such that the normal shock. Oh wait, why am I going that way? Wait, we can slow it down.
We can slow
Uh,
it down, right? In principle, we
yes, we can.
ach-
Uh,
acha. Um, Actually, it's a little interesting. Uh, Turns out you cannot. Actually, you tell me one thing. There are two tanks, okay? There are two tanks, and you connect it by a pipe, right?
okay,
And there
wait,
is
I got
one.
it. We cannot. Sorry.
You got it, is it?
Yeah, we cannot.
What did like what is what did you like what are you thinking? What did you
Yeah,
get?
means
What do
if
you think?
now we have it is converging now. Now
Hmm.
it is at some greater Mach number.
Yeah,
Now
so
it
it slows
encounters the
down.
diverging. Yeah, it slows down. Now it slows down to Mach 1. It comes to the third, it
Yeah.
is decelerated. But now, since it is already uh, supersonic, so now it will again try to accelerate if we diverge it. Uh, because now we have a diverging section
So,
again.
so the diverging section. Wait. Yes, fine. But now the flow has become subsonic, no? The diverging section will slow it further down. Do it on this thing.
You
What
need
we
to
are
brush
saying.
about the fundamentals. Yeah.
I know it's okay. I was trying to make a point. Let me just do that. I'll just quickly do whatever. Just wanted to make a point. So this is the nozzle. Now we say that we want to converge it. Wait. So this is my nozzle. This is my test section. So this is the nozzle, this is the test section. Now I converge it to sonic conditions and then expand it. So this is my diffuser. Can we have this isentropic diffuser? That is the question. Okay, I'll just go ahead and tell you. No point of discussing this thing. There are two problems with it. Suppose this happens, then the reservoir stagnation temperature and the exit stagnation temperature will be the same, right? No entropy loss means temperatures, this pressures, I'm saying temperatures, the stagnation pressures are gonna be the same, right? Right?
Yes.
Do you think a flow can sustain between two positions of the same stagnation pressure? Flow will not,
Oh.
if you think, do you get my point? The flow, anything will flow only if
Yeah.
there is a pressure difference. And to be
Yeah.
precise, it does
Pressure
not have
gradient.
to be a static, yeah, pressure gradient. It does not have to be a static pressure gradient. Sometimes it happens that there is a drop in stagnation pressure. Basically, flows anything flows from a place of high energy to low energy, or low stagnation pressure to high stagnation pressure to low stagnation pressure. So that there will be no flow if this thing is kept. You have to decrease this stagnation pressure. You have to have some losses for the flow to happen, right? Another thing, when you converge in this part of it, if you converge, let me move to try to converge a supersonic flow, what is the issue that will arise? You remember there will be
Uh,
oblique
he
shocks.
was
There will be
talking about, yeah, oblique shocks, and he was also talking about the uh, I think he was talking about boundary layer.
yeah, boundary layers interaction, all those things will happen again totally. But again, compressible boundary layers, don't know much about them, but yes, boundary layer interaction and all those things are going to happen. Maybe I don't know if it will separate or anything. I don't know. Boundary layers is a little difficult. Not gone through them, but why oblique shocks will appear?
Yeah. Due to it encounters what can I say? Virtually, the angle changes abruptly.
Yeah, angle is
So
changing abruptly. So in principle, if we want to do it, this has to be of infinite length. If we want to do it isentropically, if we do it faster, we do it, the stronger will be the oblique shocks. That is one thing. The second thing is this entire thing is fictional because you can't just neglect frictional effects. There is always going to be frictional effects, and so no matter what you do, there is going to be a pressure. This total pressure loss will always be there because friction is always there. You can't avoid that. So that is one thing. So, but again, because this is like it's a very this can't exist. You can't have this, no matter how long this section is, no matter what you do. So that is the reason why that normal shock is kept as a baseline. That is something I wanted to point out. Okay, anyways, um, let's come back to this. Yeah, so we found out this entire thing. We will find it out. Okay. Okay, let's do this one problem and then let's try to close. Consider the flow through a convergent divergent duct with an exit to throat area ratio of 2. The reservoir pressure is 1 atmosphere. Exit pressure is 0.195. Calculate the Mach number at the throat and exit. So is this problem, Pranav? Sorry, Pranay. Confused.
no, no, it's fine.
Uh,
Yeah. There
Pranav,
is a
Pranav.
throat, it's the throat. Okay. So throat to reservoir pressure is one, and
No.
okay.
So again,
Yes,
we'll
I
do
think.
one thing. We'll find out the Mach number according to that exit area to throat ratio thing. Let's do that. Okay, E divided by AE06. It's 2. Let's do this.
It doesn't seem like the Mach number would be greater than 1.
How do you know that?
Yeah. No, considering the pressure ratio. If P0 is
But
1
how
and
do
P
you?
exit is like 0.95.
Ah,
So if
okay, let's do that first. Let's see. Good question. That's a good point you raised. So let me plot that this part only, right? This is the pressure ratio plot. This is the pressure ratio plot, right? So how does this change? So we have a ratio of 1 divided by 0.95. This value corresponds to y equals to. What does this value correspond to? You get my point, right? What I'm doing right now. This is
yes,
0.293.
yes.
So this ratio corresponds to Mach number is 0.3. What is the issue of trying to figure it out this way? Let's do this. Well, okay. So Mach number is 0.293. Let's 29, just 29. Okay. So you just guessed it by having a feel for the pressure ratio, isn't it? There is another way to look at it.
Yeah.
Suppose, yeah. So the other way to look at it is find out the Mach number, which you get from. So there will be two values you will get. You will get a high value. This you get two values, right? 1.05 and no, wait. Yeah, 0.77 and 1.25. So if we go with the other way around, we will get two possible Mach values. It could be 1.25 or it could be 0.77 also. Why is it not 0.77? Because the pressure ratio will be higher. That's true. Now, if we corresponding to these two values, if we actually find out the pressure ratios, what we'll see is x equals to 1.25 and x equals to 0.77. What we'll see is that values will be 2.4 and 1.4. So again, the pressure ratios values are not matching. So this can be the more naive way of finding out that the Mach number has to be dictated by pressure ratios and not the area ratio. Okay, so because these values don't match the 1 by 0.95 value, that is fine. Just tell me one thing. Now, because Mach number is 0.29, what is the Mach number at the throat?
So 1. No, I mean, no, wait.
Cannot be 1.
Yeah.
If it would be 1, then the Mach number value will be 0.77.
Yeah, no. It's
Yeah, I
now
got it.
it's a
I got
common
it. I
notion for
just,
me.
yeah. It's a little confusing also. I'm not doing things very clearly. Anyways, so let's think about this. Yeah.
Actually, uh, when so did you calculate the Mach number from the area ratio, like from that
Hmm.
equation? So in
Hmm.
that equation, I think we consider no, wait. Oh no, nothing. I thought we do we consider Mach number 1 at any place
When we
in that
see,
formula?
yes. So in that formula, when we do this, right, when we apply this formula, this is the area ratio formula. We are kind of saying that the flow is isentropic at the throat. Sorry, the flow is isentropic and the flow is also sonic at the throat conditions. We are implying that at the minimum, in the area of minimum place, if area is changing and the flow is isentropic, then we are saying that the flow has to be subsonic at minimum, at the area of minimum, at the place of minimum area, right? Isn't it? What is happening right now? Let me open that book only.
I think it's getting diffused, I think.
Yeah, before reaching the throat, before reaching the sonic conditions, it actually gets again.
Diverges.
Let me open. Yeah,
Diverges.
it diverges. Let me just, what are we dealing with? This is Anderson. So when we calculate area ratio, what we are looking at is ME3, right? We are saying that it reaches sonic conditions, but if the pressure ratios are little lower, you won't reach there. It will be a little lower. So now, how do you calculate this thing? In absence, we know that the flow is entirely subsonic, even in the diverging part. How do we calculate the area at the exit, right? At the throat and the exit. Wait. What's the question? Question is calculate the Mach number at the throat and the exit. Yeah. See, uh, the area ratio corresponding to 0.29 is what? This is how much? Let's see. It's 2.13. Okay. Now we are also told that this is A star by AE, isn't it? Because the flow is entirely subsonic. Now we also know that A3 by AE is 0.5. Do you get this? Is this okay? And then
Uh-huh.
you're following, right? So then AT
Yes.
can be calculated to be 1.085. This is what you will get. Actually, not 85. This will be what? 65 or what? Yeah. Okay. 65, right? Yeah. Now what? Now you've gotten the area and gotten areas is fine. Now you need to calculate the Mach number at the throat and the exit. Okay. Tell me, how do we proceed?
Uh, but A star corresponds. Sorry. But
Just give me a second now. Hello? Yeah. Easy. Hmm. So we know Mach number at exit is this. Let me just 0.29. So at least Mach number at exit is found out. We need to find Mach number at throat. So right. At the throat also, see, at the throat, uh, this is actually 1.065. A mistake. Do you get this? See, because the flow is entirely subsonic and it's isentropic, A by A star value is not gonna is going to change because Mach numbers are going to be different. Okay. And because we are given that this exit area ratio is 2, we use this multiplication to find out the exit area ratio. Okay. 1.065. Now we'll feed this back in to find out the Mach number. So it's a little confusing right now, the way I have presented it, but let's see. So this value comes out to be 0.75. 0.75. Okay, let's try to understand what exactly is happening. 0.75. See, we got to know that if we would have chosen Mach number based on area ratio, we would have gotten two values which were inconsistent with the pressure ratio, first of all. So now we know that this is not driving the Mach numbers. Pressure ratio is driving the Mach numbers. And so we find out the Mach number at the exit using the pressure ratio thing, and we find that it has to be subsonic entirely in the entirety of the nozzle. So it has to be 0.29. Mach number at the exit is 0.29. For this Mach value, we find out the area ratio to be 2.13. Okay. We are also told that a throat is actually half the area at the exit. So just we were divided by half to get the area ratio corresponding to the throat area. Like just the throat location, this will be the area ratio. Using this area value, we find out the Mach number, and that Mach number comes out to be 0.75, which has to be higher than the exit Mach number, because although the flow is subsonic, but near the throat area, the flow will have to be like what do you call it? Will have to accelerate, like it exit Mach number. So that's how you calculate it. The way I've solved it is a little, maybe it can be a little confusing, but you get the gist, right?
Yeah, got that.
Or there is an issue with it.
Just to clarify, now we calculated the area exit to area. Okay, from the AE or by A star, we put 0.23
Let me draw
0.29 mark
this. Let me open this.
in the formula. Okay. I got it. What? Okay.
Got it properly, is it?
Yes.
So if this were the situation. So this is the situation, right? We know the flow the entirety of the flow is subsonic. Now, as the area changes, we know A star is not going to change. That we know. A star value is not going to change. So A star, yeah, I should have written it this way. A star of exit equals to A star of throat. That makes the things clear, right? Because we know that there is no shocks or anything, so we know that the A star values will remain constant. A star value will be constant, right? Using that, we find out the Mach number at the throat. So would be like what would be happening is, use this drawing to me. Can't use it, is it? So if this is Mach number, it will be 0 at the reservoir. It will increase to 0.75, 0.75, and then it will slow down, because again it's subsonic flow. So Mach number increases, but then Mach number decreases, and this value is 0.3. You get it, right?
Yes. I got that.
So because it's 8 o'clock now, I'll stop. Rest of it, we'll see if I'll continue it in the next time, or we'll continue with the next session, like next video, like this week's discussion. Okay. So okay, okay, Pranav, we'll meet next time.
Yes. Thank you, sir.